World War II revealed a fundamental limitation in modern warfare. Radar could detect enemy aircraft at long range, but detection alone did not produce effective defense. Information arrived faster than human operators could process it. Targets changed position while calculations were still being made. Errors accumulated, delays increased, and by the time a response was issued, the situation had already shifted. The problem was not visibility, it was reaction time. Military systems relied on humans to interpret data, predict motion, and correct error. Under real combat conditions, this approach could not scale. As aircraft speeds increased and engagements compressed into seconds, human reaction became the weakest link in the system. Defense remained reactive, always responding to where the enemy had been, not where it was going. Norbert Wiener addressed this limitation by redefining how control systems should function. Instead of relying on delayed human decisions, he developed a framework in which machines could predict target motion, measure error continuously, and correct their behavior automatically. His work introduced feedback and prediction as central elements of system design, allowing machines to act based on future states rather than past observations. This shift transformed air defense from a sequence of human actions into an integrated predictive system. Decisions no longer depended entirely on operator speed. They depended on systems designed to anticipate change, correct themselves, and operate continuously under pressure. These principles did not appear on the battlefield as weapons. They existed inside equations, control loops, and invisible system architectures that determined whether defense could act in time at all. Norbert Wiener was born on November 26, 1894, in Columbia, Missouri, United States. He grew up in an academic household shaped by his father, Leo Wiener, a linguist and professor at Harvard University. Education was treated as a structured discipline rather than a personal choice. From an early age, Wiener was trained to work with formal reasoning, strict study schedules, and intellectual precision. His upbringing emphasized analysis, logic, and measurable progress, rather than creativity or experimentation. Wiener demonstrated exceptional intellectual ability during childhood. He entered Tufts College at the age of 11 and completed his undergraduate studies in mathematics before reaching adulthood. He then continued his education at Harvard University, where he earned a doctorate in philosophy and mathematics at the age of 18. His early academic work focused on abstract mathematical problems, including probability theory, logic, and stochastic processes. At this stage, his research had no connection to engineering, military systems, or applied technology. After completing his doctorate, Wiener pursued an academic career. He held teaching and research positions, and continued to publish in theoretical mathematics. His work was highly technical and largely disconnected from physical systems. He did not design machines, build hardware, or participate in industrial research. He was known primarily as a mathematician whose work operated at a conceptual level rather than an operational one. This situation changed with the onset of World War II. As the conflict expanded, the United States faced growing challenges in air defense. Radar systems were capable of detecting incoming aircraft at long range, but detection alone did not translate into effective interception. Aircraft moved quickly, radar data arrived continuously, and human operators were required to interpret information, predict trajectories, and issue commands under severe time constraints. Delays introduced error, and error reduced the effectiveness of defense systems. Military researchers recognized that improving individual components was insufficient. Faster radar or stronger weapons did not solve the core problem. The limitation was systemic. Human reaction time, combined with noisy data and delayed feedback, prevented defense systems from scaling as threats increased. Predicting where a target would be in the future became more important than knowing where it had been. Wiener was brought into wartime research efforts focused on anti-aircraft fire control. His role was not to design weapons or improve radar hardware. Instead, he was tasked with addressing the mathematical and control problems underlying prediction and response. Specifically, Wiener worked on how to estimate future target positions using imperfect information while accounting for delay, uncertainty, and continuous motion. In this context, Wiener began treating air defense as a control system rather than a sequence of human decisions. Radar measurement, tracking, aiming, and firing were analysed as parts of a single loop. Errors were not treated as failures, but as measurable signals that could be used to correct future behaviour. This approach required abandoning the assumption that humans would remain at the centre of every decision step. Wiener applied mathematical tools from probability theory and signal analysis to model target motion and system response. He focused on how systems could continuously compare predicted states with observed data and adjust their output accordingly. This framework allowed machines to compensate for delay and reduce the impact of noisy measurements. Prediction became a built-in function rather than an external calculation performed by operators. Through this work, Wiener transitioned from pure mathematics into applied systems theory. He was no longer focused solely on abstract proofs, but on how mathematical structures could govern real-world behaviour. His contributions addressed the core limitation of air defence, the inability to act quickly enough using human-centred control alone. By formalising feedback and prediction, Wiener helped define systems capable of acting faster than manual processes allowed. These ideas laid the foundation for what Wiener later termed cybernetics, the study of control and communication in machines and living systems. During the war, this was not a philosophical concept. It was a practical response to operational failure. Systems that could predict, correct error, and adjust continuously were essential to reducing uncertainty and improving response time. By the end of this phase, Wiener was no longer operating solely as an academic mathematician. He had become a key contributor to wartime system design, focused on prediction, feedback, and control. His work addressed how decisions could be supported before engagement occurred, rather than after failure was observed. These principles would later influence a wide range of technologies, but their first critical application was in the effort to overcome the limits of human reaction in modern warfare. The core problem Norbert Wiener addressed during World War II was not detection, but prediction. Radar systems could measure the position of an aircraft at a given moment, but air defense depended on knowing where that aircraft would be when a response occurred. Between measurement and action, time passed. During that delay, the target moved. Any system that relied only on current data was already operating too late. Anti-aircraft fire control highlighted this limitation clearly. Radar provided noisy and intermittent measurements. Human operators were required to interpret these signals, estimate speed and direction, and aim weapons accordingly. Each step introduced delay and additional error. As aircraft speed increased, this process became increasingly ineffective. Even small timing errors produced large spatial errors at long range. Wiener approached this problem by treating air defense as a dynamic system governed by continuous feedback rather than discrete decisions. Instead of relying on operators to manually extrapolate target motion, he focused on how systems could automatically estimate future states based on past and present data. This required formal methods for dealing with uncertainty, delay, and noise. To achieve this, Wiener applied probabilistic models to target motion. Radar measurements were treated as imperfect observations rather than precise facts. The system's task was to combine these observations over time, identify patterns, and estimate the most likely future position of the target. Prediction was not a one-time calculation. It was a continuous process, updated with every new measurement. Feedback played a central role in this framework. Wiener modelled air defence as a loop in which predictions were constantly compared against new observations. The difference between predicted and observed position represented error. This error was not discarded. It was fed back into the system to refine future predictions. In this way, the system could correct itself continuously rather than waiting for human intervention. This approach marked a fundamental shift in system design. Traditional control relied on operators reacting to events after they occurred. Wiener's framework allowed systems to act based on anticipated future states. Control became proactive rather than reactive. The system was no longer chasing the target's past position. It was adjusting itself toward where the target was expected to be. Wiener's work also addressed the issue of delay explicitly. In real systems, time delays could not be eliminated. Radar signals took time to process. Commands took time to execute. Wiener incorporated delay into his models rather than treating it as an error source to be ignored. By accounting for delay mathematically, systems could compensate for it instead of being destabilized by it. These ideas were applied to the design of predictors used in anti-aircraft systems. Although the hardware varied, the underlying logic remained the same. Estimate motion, predict future position, measure error, and correct continuously. The effectiveness of the system depended less on the skill of individual operators and more on the stability of the feedback loop. Wiener's contribution did not result in a single machine bearing his name. It resulted in a design philosophy for control systems. Prediction and feedback became core requirements rather than optional enhancements. Systems were evaluated based on their ability to remain stable, accurate, and responsive under continuous operation. This framework extended beyond air defense. Any system involving moving targets, delayed response, and noisy data faced the same challenges. Wiener's work provided a general solution applicable to tracking, guidance, and automated control. During the war, this meant improving the effectiveness of defense systems under extreme time pressure. By formalizing prediction and feedback, Wiener helped remove human reaction time from the most critical part of the control loop. Operators remained involved, but they no longer carried the full burden of real-time calculation. Decisions could be supported by systems designed to operate faster and more consistently than manual processes allowed. This shift did not make systems infallible. It made them scalable. As threats increased in speed and complexity, systems based on Wiener's principles could adapt without collapsing under delay and error. This capability defined the transition from human-centered control to system-centered anticipation. The practical effect of Norbert Wiener's work was a shift in how military systems were evaluated. Success was no longer defined only by detection range or firepower. It depended on whether a system could respond within the shrinking time window imposed by faster aircraft and longer engagement distances. Prediction and feedback became the limiting factors of effectiveness. In anti-aircraft defense, systems influenced by Wiener's principles were better able to handle continuous streams of radar data. Instead of resetting calculations with each new observation, predictors maintained an internal state that evolved over time. This allowed defenses to remain coherent, even when measurements were noisy or intermittent. Stability replaced improvisation. The importance of this approach extended beyond individual weapon systems. Air defense networks increasingly relied on coordination between radar stations, predictors, and command centers. Information had to be processed continuously and shared across multiple nodes. Systems that treated each update as an isolated event failed to scale. Systems designed around feedback and prediction remained stable as complexity increased. Wiener's influence was especially visible in the transition toward integrated command and control structures. Decisions were no longer made solely at the point of contact. They were distributed across systems designed to anticipate threat behavior. This reduced reliance on individual operator skill and increased consistency across operations. Human judgment remained important, but it operated within a framework shaped by predictive systems. Although many of the large-scale systems associated with these ideas reached full maturity after World War II, their conceptual foundations were laid during the conflict. The problems Wiener addressed, delay, uncertainty, and continuous motion, were wartime problems. The solutions developed in response to these constraints shaped the design of Cold War defense systems, rather than emerging independently later. Beyond air defense, Wiener's work influenced the development of guided systems, automated tracking, and control mechanisms in multiple domains. The same principles applied to navigation, industrial automation, and communication networks. Any system that required stable behavior under continuous input benefited from formal feedback and prediction. Wiener was careful about the implications of his work. He understood that systems capable of anticipating and correcting behavior reduce the role of direct human control. This raised ethical and strategic questions about automation in warfare. While these concerns became more visible after the war, they originated in the realization that machines could operate faster and more consistently than human operators under certain conditions. Despite these concerns, the military significance of Wiener's contributions lay in their restraint rather than escalation. His work did not enable autonomous destruction. It enabled controlled response under time pressure. Systems based on feedback and prediction reduced randomness and prevented collapse when conditions became too complex for manual control. By the end of World War II, it was clear that future conflicts would not be decided solely by superior weapons. They would depend on systems capable of processing information, anticipating change, and acting within narrow time margins. Wiener's work addressed this reality directly. He did not provide tactical advantage at a single moment. He reshaped how systems were designed to function before engagement ever occurred. Norbert Wiener's legacy is therefore not tied to a specific device or battlefield victory. It lies in the transformation of control from reaction to anticipation. By formalizing prediction and feedback, he contributed to systems that decided outcomes long before physical contact was made. This shift defined modern warfare at the system level and remains embedded in military and civilian technologies today.